Okay, hello, Precalc C. It's Thursday afternoon, and in class 7, period 3 and 4, we learned about parametric equations. Specifically, we tried to talk about the entire idea of parametric equations, kind of inspired by physics, when there are times when you would like to describe the motions of an object that is moving around in 2 dimensions or possibly even 3 dimensions independently as with sort of separate equations describing each of the coordinates. And so you can think of what we're doing here with parametric equations as a kind of exploration of that. There are many sort of mathematical phenomena. There are many kind of mathematical curves which are inspired by perhaps inspired by physics, in which it is more convenient or possibly even more, I don't know, coherent or something to describe the x and y coordinates of a point on that curve independently with 2 different equations. And okay, anyone who's watching who's not in my class, this year we're sort of starting in the middle of this lecture. We've been graphing a whole bunch of parametric equations. And so for my own students, this lecture is now continuing. So here's an example of a parametric equation. This was the next one on the handout that we didn't get to in any of the classes, at least on Thursday. And okay, we'll just kind of going over what's going on just a little bit. Yeah, we have a pair of equations, x equals some stuff, y equals some stuff. And the idea here is that there's an independent variable t, and unless specified, or unless it turns out to be the case that t doesn't work, or that these equations don't work for certain values of t, by default we are taking the value of t to be just a real number. So we are open to the idea of t being any real number from negative infinity to infinity. And here we have a formula for x in terms of t and a formula for y in terms of t. So t is the true independent variable here, and the x coordinate is a function of t, the y coordinate is a function of t, and so we have some object which is moving with a certain x and y coordinates which have been described here. And the goal of this entire exercise is to understand, I suppose, what curve is being defined by this parametric equation, by this pair of parametric equations. And to be sort of to say it another way, if you think of t in terms of time, and you think of this object as sort of moving in the xy plane with these 2 coordinates, then the goal here is to sketch a picture of the path that object takes. With sort of sufficient annotations such that one may kind of understand everything there is to know. Alright, let's just go into this problem. What do we see? Well, okay, here I said that we should consider values of t from negative infinity to infinity, but the so-called natural domain of this function is going to restrict that in some kind of way. So that's sort of the first step, is note the restrictions. What are the restrictions? Well, I can't take the square root of a negative number, so it's better be the case that the inside here is positive, and the only way for negative t to be positive is if t is less than or equal to 0. Okay, so I sort of determine kind of naturally from looking at the function that this function is only valid for negative t values. Okay, and 0. And yet, if I take the square root of any number, I'm always going to get something positive, and therefore this square root of negative t is going to be a positive number. So if I'm adding a positive number to negative 3, then x has got to be bigger than or equal to negative 3. And furthermore, well, if t is going to be negative, then the opposite of t is going to be positive. So I can say that y is going to be greater than or equal to 0. So this is the sort of the first step, which I think is important, is to note your what I call restrictions. The restrictions are merely, well, they're just observations about the domain. You sort of note what t values are invalid. and you make any kind of observations you can about x and y. Okay, the next thing to do is to look at end behavior. And so in general, we're going to, for these problems, we shall look at the behavior of x and y when t is huge. But okay, this one is just irrelevant because in fact, there is no right end behavior. There's no such thing as talking about when t goes to infinity because t must be negative. So we have only really this case to consider. Well, okay, what does happen as t approaches negative infinity? So if you give me some huge negative number, negative a million or something, well then that gets multiplied by -1. So it becomes positive, and the square root of a big positive is still a big positive. So x is going to infinity. And okay, if t is a huge negative number, then y is also going to infinity because y is just negative t. Okay, well, all right, now that I've done that, and I do think it's important to do that first, let me now eliminate the parameter. And to eliminate the parameter, I solve for one of the equations in terms of the other one. So, okay, here it seems like the thing to do is to take this equation, add 3 to both sides, then being a little careful here, I'm gonna square, so I get x plus 3 squared equals negative t. But then, of course, y is negative t, and so this tells me that y is x plus 3 squared. Okay, and so I've performed this kind of algebra move. What does this algebra move do? It determines the relationship between x and y. And okay, all the examples that we saw in class, and this example as well, it turns out that the relationship between x and y is like some well-known relationship that we already are familiar with and understand, so that's nice. So here, what this tells me is that the path that this object takes through the xy plane, the relationship between x and y, is determined by this quadratic equation. Okay, and I know how to graph this quadratic equation. It's going to be a parabola which has been shifted 3 to the left. But looking at my restrictions, I see, well, it must be the case that x is greater than or equal to -3. And so if I trust that, it seems that only the right half of this parabola is truly happening. And can I make some kind of sense of this? Yes, I can, by some careful amount of point plotting and stuff like that. Let's see, what are the valid numbers I'm allowed to plug in? Well, negative numbers only. So if I plug in 0, say, for t, I get -3, 0. Okay, so here t equals 0, -3, 0. What else? I can plug in -1. If I plug in -1, then negative 1 is 1, square root of 1 is 1. So I get -2, 1. Alright, I think I'm starting to get a kind of sense of this now. What's another good number to plug in? Well, -4. If I plug in -4, -4 is 4, so that's 2 minus 3, so that's -1, +4. Is when I plug in t equals -4. And I'm now catching on. If I plug in t equals -9, I will get 0, 9. And so, what's happening here is kind of interesting. This is similar to the two problems that we did in class, the last two problems we did in class, but also kind of different because now, because t must be negative, this curve, this pair of parametric equations is sketching out, once again, the right hand side of this parabola, but in a different way from the one we saw in class. Now, as t approaches negative infinity, I am up here at the edge of my parabola, you might say. And now, as time moves forward, and that's what these arrows are meant to indicate, from negative infinity to 0, I move down the right edge of this parabola, and I kind of stop at the vertex -3, 0. Okay, so for my own students who are watching, this is kind of the end of the intro, so to speak. All of these were, I don't want to say easy, but they were, doable. Now it just starts getting kind of crazy, and I think one thing that's really sort of fun about these parametric equations is sort of how difficult it can get. So let's do another one. This is also a little bit of a sad moment because, you know, this is one of the classes with very little lecture, and it's just kind of, you know, usually 90 whole minutes of just students just kind of working independently with small bits of help from me, you know, together in groups and kind of talking it out. And so it's really sad to be doing this via video, because you should really try this problem on your own. I think that's when the learning comes, is from trying this. But okay, I'll stop saying this over and over again, but the responsible thing to do right now, I don't know if that's what I would do if I were you, but the responsible thing to do would be to pause this video and at least try for a couple minutes to figure this out, because it's less fun if you just watch. But alright, here we go. We have a pair of parametric equations. This is quite interesting. What can we make of this? Well, straight away, I would like to investigate the restrictions. I think that is important to sort of do first. Well, what are there? Well, I can take the sign of any real number, so therefore there are no restrictions on t. Are there some restrictions on x? Well, yes, because this being a trig, sinusoidal trig function, it's bounded. And okay, you can almost do this in your head, but I think this is a nice follow-up on some of the things that we were doing, you know, in the last couple of weeks. Fact, sine is between -1 and 1. That's just a fact of the sine function. And if that's true, then, well, it is true, then 2 sine t is going to be always between -2 and 2, of course. That's just the amplitude of the trig function. Well, what can I say about 2 sine t minus 3? It will be between -5 and 1. Okay, and so, what have I just determined? I have just determined that the x-coordinate in this problem is guaranteed to be between -5 and 1. Alright, so that's like good information to just know right off the bat. What else? Can I perform a similar analysis on the y-coordinate? I think I can. Because, alright, what do I have to say about sine? Well, once again, it's between -1 and 1. So, if sine is between -1 and 1, then what can I say about sine squared? Okay, this requires a little bit of thinking, but if you square a number, which is between -1 and 1, then the square of a number between -1 and 1 will be between 0 and 1. Okay, I won't justify the logic behind that step, but okay, that's just certainly true, right? If sine is positive and less than 1 and you square it, it's less than 1. And if sine is negative, but in between -1 and 0 and you square it, it's also less than 1. Okay, well, multiply through by 4, and that tells me that 4 sine squared t is going to be less than or equal to 4. And so just straight away, I have that my y-coordinate is between 0 and 4. Okay, so this is going to be unlike the first 5 sets of parametric equations we graphed, because in this case, the shape, the path that this object takes through the xy plane, the graph which is sketched out as t changes, is going to be a bounded graph, right? It's a graph which stays within some kind of rectangle of some kind. Okay, well, let's put that thought aside, and the next step in the algorithm is to look at the end behavior. But, okay, here in this case, we're just going to skip that step, because there is no end behavior to speak of. What happens as t goes to infinity? Well, we know that the trig functions simply just oscillate up and down. And so, in fact, x is just going to go up and down, back and forth, between -5 and 1 forever. So there is no end behavior in the sense that there is no particular value that that x is getting closer and closer to as t gets very, very big. And the same thing with y, right? What happens as t increases or decreases? Rather, both off to infinity, well, y is just going to be going up and down between 0 and 4. Okay, so I get no information out of that, so I'm just going to skip right to the step of eliminating the parameter. Okay, so I'll start with x equals 2 sine t minus 3, and I'm going to eliminate the parameter. Now, alright, when this happens live in class, I've seen what people do. They sort of add 3, and then, alright, you know, kind of feeling that the eliminate the parameter step has been sort of taught to you as, you know, solve for t in one of the equations and stick it in the second equation. if that's your conception of what we're doing here, then you might feel sort of obligated to divide by 2, and then even to, you know, maybe do some kind of arc sign, you know, discussing something like that. But of course that's not needed, because there is no rule that says that we need to solve for t explicitly. All we are doing is just, you know, eliminating the parameter one way or another. And of course, if x plus 3 is 2 sine, then what is y? Well, y is just 2 sine quantity squared. In other words, just square both sides right now, I think is the better thing to do, and you get x plus 2 squared equals 4 sine squared t. Okay, well, that's just y, and so it turns out, okay, this is a little bit of a running joke or something. Once again, obviously if we were live this would go better, but some people are shocked, dismayed, ironically happy that this is now the same equation again. This same y equals x plus 3 squared. Could it be really just our same simple parabola that has been moved 3 to the left? Well, kind of. And now let's just go graph that parabola. Yeah, it sort of is just that same parabola, which has been moved 3 to the left. And here we reach for the restrictions that we established while doing this preparatory work over here, and see that, well, the x-coordinate is going to be between -5 and 1. And so, all right, well, because I've been graphing this parabola already kind of multiple times, I know that when x is -5, the y-coordinate is 4, so that is the point -5, 4. And when you plug in -1, you also get 4, so that's the point -1, 4. And so it seems that the relationship between x, y is determined by this parabolic relationship, but somehow my x-coordinate is sort of bound in between -5 and, I should say -1, right? Yeah. Sorry about that. Yeah, of course, the x-coordinate is trapped between -5 and -1, and the y-coordinate is trapped between 0 and 4. And so this is actually just what we get. What is the shape? It is a truncated parabola. Okay, how could this parabola be truncated? Why? Why is it truncated? How do I not, you know, what happens because I'm allowed sort of an infinite number of t values? Why do I sort of stay in this small little region, you might ask? Well, I think the key to everything is doing some point plotting and sort of figuring out what's going on. So let's do that now. What are some good values to plug in? Well, if I plug in, say, 0, sine of 0 is 0. So if I plug in 0, I get, well, I get -3, 0. Okay, so that's kind of nice to know. Here I am at the vertex of this parabola at time 0. Okay, what's the next nice thing to know? I mean, there's a bunch of things we could do. Let's just plug in pi over 2. If you plug in pi over 2 for sine, what do you get? Well, sine of pi over 2 is 1. And so we get -1, 4. Okay, so here I am at t equals pi, here I am at the points -1, 4 at t equals pi over 2. And so it appears that I've gone sort of from here to here. And alright, usually there's not enough time for this in class, but maybe we should do another thing, because there's one more number that sort of goes in here nicely. That's when sine is 1/2, which happens at pi over 6. And is that what I want to do? Yeah. So if I plug in pi over 6, sine of pi over 6 is 1/2, and I get -2, 1. So that might be something maybe that you want to do. That's the point -2, 1 at t equals pi over 6. Well, okay, this is just giving every indication that I start here, I sort of go up and up to here, but now what happens? Okay, well maybe now I should skip to my next sort of nice value, maybe pi. Well, sine of pi is 0, and so that just puts me right back at -3, 0. So I'm not only at the point -3, 0 when t equals 0, but also at t equals pi. Okay, I think I'm starting to see what's going on here. What about 3 pi over 2? Sine of 3 pi over 2 is -1, so that makes that -5. And here the -1 gets squared, so -5, 4. So I'm over here at t equals 3 pi over 4, and then, sorry, 3 pi over 2. And then what happens by the time I get back to 2 pi, I'm back again here. Alright, so I think I already have sort of seen enough to get the general gist of what's going on. I'm going to start here at 0. Between 0 and pi over 2, I'm going to go zoop zoop. Then between pi over 2 and pi, I'm going to go back. Between pi and 3 pi over 2, up. Between 3 pi over 2 and 2 pi, back. And in fact, this whole thing is just going to go zoop 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 forever. So that's the whole thing, and it actually makes kind of sense in a certain way, because after all, these restrictions didn't come from nowhere. They came from the fact that x is just operating like some kind of sinusoid, and y is operating like the square of some sinusoid, which is also a sinusoid, by the way. That's just when you sort of have an object which is moving in this fashion. The outcome is a parabola, which maybe is kind of also sort of interesting. All right, you can add more things if you want to be like a superstar. You can realize that actually I will be also back at this point at 5 pi over 6, because pi over 6 and 5 pi over 6 have the same y coordinate on the unit circle, so they will have the same sign values. And this point over here, this negative 4, 1, that's going to happen at 7 pi over 6 at t equals 7 pi over 6, and again at 11 pi over 6. You can just trust me on that, or you can just do it yourself. Sine of 7 pi over 6 is negative a half, so that becomes negative 4, and 1 again. Okay, so this is all just good. Probably the last thing left to do is, you might be thinking, how am I possibly going to add arrows to this figure, which I think is a key part of the sort of requirements. There's no real good way to do this, because if you drew arrows going all which way, that would just be kind of incoherent. So what I do is I just kind of create this auxiliary little shape just to kind of tell the world, hey, this thing's going, you know, up, and then sort of back, and then sort of back again, and then, you know, like this. So that's my kind of compromise. Okay, that was number 6. What do we have left? 3 more to go. Maybe we'll even do the last one. So I thought this was pretty hard. 7 is just like even more hard. And I think this has got some like new stuff in it. So I mean, everyone, you really need, in my class, you really need to keep watching. Okay, number 7. Let's go. What is this problem? Well, it's x equals 1 over t minus 3y equals 1 over t squared. Okay, this seems pretty hard. How are we going to do this? Well, we should be careful. Okay, so let's first note our restrictions. Well, I got a big restriction right now, which is that t can't be 0. So once again, I'm open to t being any real number, but the natural domains of these two expressions, x and y, exclude 0, so definitely t can't be 0. And now, I noticed something. Look, if t can't be 0, well, t can't be 0, so this fraction is always something, right? It's never 0. So if this fraction is never 0, then I'm basically adding something else to negative 3. And therefore, x just can't be negative 3. That's just true. And, of course, y is going to be positive because it's 1 over t squared, but also it can't be 0. So y has to be greater than 0. And now, okay, great. Now let's do the end behavior step. So let's see, okay, considering what happens as t goes to infinity and t goes to negative infinity, the order doesn't matter. I don't know why I do it backwards like this. Sometimes I feel like finding the positive infinity case is somehow easier, so I like to do that first. Alright, well, this requires a lot of kind of advanced, calculus type thinking that I hope we're getting better and better at with practice. As part of the rationale for doing this activity. What happens as t goes to infinity? Well, if t goes to infinity, that's like a really big positive number. That's like 1,000,000. what can I say about 1 over a million? 1 over a million is very, very tiny. It is a tiny positive number. And when I add a tiny positive number to -3, what do I get? Well, I get basically -3, but it's going to be a little bit more than -3 because it's -3 plus a tiny positive number. So I indicate this with this little plus. We've used this before, but I'm using it now sort of again. You should understand this little superscript plus as meaning x is going to a number which is a little bit more than -3, so -2.9, something like that. Okay, what about y? Well, if you give me a million squared is even bigger. 1 over a huge positive number is a tiny positive number. So y is going to 0 plus. What happens as t goes to -infinity? Well, now being kind of careful, if t is like -1,000 or something, then 1 over -1,000 is going to be a tiny negative number. And if I add a tiny negative number to -3, it's still pretty much -3, but it's going to be a little bit less than -3. So I put that little negative up there to indicate that it's -3 plus a tiny negative, which makes it a little bit more negative, so -3.1, say. Okay, and what happens to y? Well, now, still, because we're squaring here, if you give me a huge negative, -1,000, say, and you square it, you get positive a million. And 1 over positive a million is going to be tiny, but positive. Alright, I thought that was kind of hard a little bit, or at least, you know, at some point it becomes kind of automatic, but this, if you're new at this sort of reasoning, this is good exercise, so there it is. Okay, so that was kind of the big part. I will say one more thing, which is, personally I find it more comfortable to just do what we just did, which is to sort of algebraically analyze the formulas. But potentially, so I'll call this optional. Some teachers require this, but I think it's excessive to force you to do this, but I encourage you to do it if you want to, which is to make separate graphs for x and y, actually just to kind of help you with what's going on. Actually, wait, hold on, I forgot one thing. Okay, so I'll finish my thought. My thought was that potentially you might be comfortable or might find this everything we've just done sort of easier if you made a graph of what happens to the x-coordinate and a graph of what happens to the y-coordinate. In other words, if you want, you can lean on your sort of knowledge about the 1 over t minus 3 function to make a picture of what the x-coordinate is doing sort of as a function of t. And I put t on the horizontal axis kind of by default because t is like the independent variable, and so we're looking at what happens to x based on t and what happens to y based on t. Before I do that, I almost forgot that there's something else we have to do here, right? So we were on the end behavior step, and this end behavior step, you know, seems like we did our job, but I say we are only half done. Because the end behavior step is has another part to it, and the other part of the end behavior step, which hasn't come up yet, but I really feel strongly you should do it now, is to not just investigate the behavior of x and y near when t is getting huge, because usually when t is becoming sort of infinitely big, you know, something interesting is happening. But we must also investigate x and y near any other values where they are sort of getting crazy. So is there some other kind of crazy infinite-like behavior? And the answer is yes, right? Near 0, things are getting crazy. So of course at 0, these two things are undefined, but near 0, x and y are both sort of exploding in giant size. And so what we need to do now is to investigate the behavior of x and y near as t approaches 0. And it should be clear to you that it really, really matters whether t is a tiny positive number or a tiny negative number. And so, okay, the thing to do now is this sort of just like obligatory step that I'm adding to the other obligatory steps is to consider the behavior of x and y near places where t is undefined or exhibits kind of infinite behavior. And so, okay, as t approaches 0 plus, what's going on? Let's just do it now. If t is a tiny, tiny positive number, then 1 over a tiny, tiny positive number is a huge positive number. And so x is going to infinity. Okay, yeah, like if you give me 1 over a million, then 1 over 1 over a million is like a million. All right, and what about y? Now if you give me a tiny positive number and square it, it gets even tinier. And so 1 over that is going to be, even huger or something. So we get this. And as t approaches 0 minus, which is to say, when t is a tiny negative number, what is 1 over a tiny negative number? It's a huge negative number. So x is going to negative infinity. And if t is a tiny negative number and you square a tiny negative, it becomes an even tinier positive. So 1 over a tiny positive is a huge positive. All right, I really do think this is, quite hard. But you sort of get better with practice and thinking this out. So maybe, if that was too fast for you, go back and watch it at 1 time speed until you understand it. And here's what I was kind of saying a few minutes ago, which is that potentially you could argue that it would be easier on your brain if you just made pictures of these. So what does 1 over t minus 3 look like? Well, it looks like, I know what the 1 over t function looks like. It kind of has that zoom shape, and then the whole thing is being moved down 3. So it's going to look like this, and yeah, it's just going to kind of look like that. So here I am just using my basic pre-calculus knowledge to produce a graph of 1 over t minus 3. And why is this helpful? Because now this kind of is a picture of what the x-coordinate is doing. And how about y equals 1 over t squared? We've seen this before also. This is volcano, because this is just reciprocal of a parabola. And so we get this kind of shape. All right, why is this nice? This is nice because this, if you were sort of, if you took the initiative to make these graphs sort of first on your own, then this is telling you very obviously, okay, of course x can't be negative 3. Here it is, right? There's no value of t which will make x negative 3. Of course y has to be positive. And then you can sort of read these off those pictures, right? So what happens as t goes to infinity? Well, for very, very large t values, yeah, look what we find. X is a little bit more than negative 3. Y is a little bit more than 0. How about as t approaches negative infinity? Just looking at my two graphs, I see, well, yeah, x is going to be a little bit less than negative 3. Y is going to be positive. How about if t is a tiny positive number? Well, yeah, they're both going to infinity. And if t is a tiny negative number, x is going to negative infinity and y is going to infinity. So if you want, you can simply do this every time. It's just a whole nother step, I guess. So I'll call it optional. But it can help you make these end behavior charts. Okay, having done all that, we're ready to eliminate the parameter. And here I think I know what to do. Once again, x equals 1 over t minus 3. Okay, here come the groans, except no one is here to do the groaning, so I guess there'll be no groans. X plus 3 is 1 over t, but then if I just square both sides here, I get x plus 3 squared equals, when I square, 1 over t, of course I just get 1 over t squared, and that's just y. So, here we have yet another example of the, supposedly, just the same problem again, and I'm sort of making a point that, though eliminating the parameter is really just one tiny part of doing these problems, because, okay, I think you know what I'm talking about, so let's just do it now. How are we gonna do this? Well, there's some kind of parabola, and let's see, what should I do? Well, I'll just graph it, I suppose. 4, 5, 6. And, well, what do I know about this parabola? It's got that sort of same shape. We've now done this already 6 times or something. So, yeah, happy parabola. Just stick that in there. Cha-cha. Okay, so kind of what? All right. Now the thinking begins. So how does this path? This is the path of the object, but how does it happen? And maybe the thing to do is go in chronological order. So let's start at time negative infinity. Where am I at time negative infinity? Well, I am a little bit to the left of -3, comma, tiny positive. So that means somehow I'm here. Oh, okay, maybe another thing to mention is that, in fact, x can't be -3. So this sort of spot on the graph is wrong somehow. Also, y has to be positive. It can't be 0, so that's kind of mysterious. And I'm starting to get a kind of sense of this because at time negative infinity, when t is like -1,000,000, I am very, very close to that vertex. In fact, this vertex is some kind of just like, you know, pit of despair or something like that, right? Here I am at t equals negative infinity. Maybe I should draw it on the other side. At time t equals negative infinity, I'm kind of like stuck somehow in this pit, and it's sucking me down or whatever. But then what happens kind of over time is I think I move up it. In fact, what seems like maybe a good number to plug in? How about -1? If I plug in -1, what do I get? 1 over -1 is of course -1, so it's like -4, comma 1. Whoa. This is blowing my mind. Because what it means is that it took me from time negative infinity to get from the vertex of this parabola up to this point at -4, 1. So this tiny little thingy right here, that took sort of an infinite amount of time, from time negative infinity to time -1. So it appears that we're moving, you know, kind of up this parabola, cha-cha. Okay, what's another nice number I could plug in? I don't know, I could plug in like a half, say, if I want to be kind of some sort of superstar here, right? I plug in a half, what do I get? Well, 1 over half is 2, so it's -1, a half squared is a fourth, so that would be 4. So -2, 4. -2, comma 4. Oh, wait, something went wrong. No, if I plug in what did I say? If I plug in negative a half is what I kind of meant to say. Yeah, negative a half. 1 over negative a half is 1 over negative a half is -2. So I get -5, 4. Because I do want to go in chronological order. So this is time t equals negative a half. Okay, so it takes me from time negative infinity to time -1 to do just a little bit, and then in a half a second I do this little bit. Okay, and now things go completely insane, because as t approaches 0 minus, in fact we shoot off out to negative infinity times infinity. And so here I'm going to label this t equals 0 minus, and in fact what is it that really happens now? The answer is, where do I end up at t equals 0 plus? Oh, at infinity, comma infinity, so over here. Okay, so some sort of ridiculous, infinite, time travel, teleportation type thing happens from this point to this point. And so I'm going to label this with a teleporter. This is like official, this is official. Someone asked me one year, Mr. Rose, is this just some crap that you made up, or is this industry standard? This is industry standard. Teleportation occurs from t equals 0 minus to t equals 0 plus. Actually, both are true. That I made it up and that it is industry standard. So what's happening here? We're sort of moving from time negative infinity, from the pit of despair, up the left half of the parabola, and then in the 1 second it takes me to get from t equals -1 to t equals 0, I'm doing almost the entire parabola off to infinity, that instant teleportation from time t equals 0 minus to time t equals 0 plus to the top half of the parabola, where I then sort of now go back down again, which can be seen by plugging in some more numbers, like say, t equals 1/2 now is kind of what I meant to do. If I plug in t equals a half, 1 over a half is 2, so I get 2 minus 1, -1, 4. t equals 1/2 at negative 1 comma 4. And I guess I could do t equals 1. Where am I going to be at t equals 1? I will be at negative 2, 1. So here I am at t equals 1, negative 2, 1. So once again, it took me 1 second to get from all the way infinitely out on this parabola down to this point, and now I'm just a little zoop zoop away from the pit of despair vertex. But how long does it take me to get there? An infinite amount of time, right? Where is it? Here. As t approaches infinity, I get slowly closer to the point negative 3 plus. In other words, I will label this sort of location right here just immediately to the right of this thing as t equals infinity. And that is my way of indicating that as we approach infinity, we get sort of closer and closer to that vertex. Alright, so this is quite kind of crazy. If you want to kind of do this out with your finger or something, it's like you start here, an infinite amount of time goes by to get here, and then it's like zoom, 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 and then infinite amount of time to slowly go back down towards the origin. Alright, so that was really important. We're going to try to do 2 more of these in the next like 10 minutes or something. And maybe we won't do number 10, because that's quite a kind of crazy challenge. But this one I think was really important. Okay, here we go. 8 and 9, and then we'll call it a day. So, yeah. Number 8. What is number 8? X equals ln t minus 3, y equals ln t squared. Dude, Mr. Rose, you seriously expect me to like know facts about the natural log function? Yeah. That's the whole point of this activity, is to just become really good at this sort of thing. Maybe this is sort of second nature to you. Well, what is true about the natural log function? What does maybe I'll do this now. What does the normal natural log function look like? What is just ln t? Well, the natural log function is a log function, so it's going to look like every log function looks, which is it's the inverse of an exponential function. So if the e to the x function looks like that, then the natural log function is going to be the reflection of that graph across the line y equals x. And since e to the x is always positive, natural log takes only positive numbers. If you plug in 1, so, the natural log of 1 is 0. And so, I don't know, maybe that's good enough for now. I'll just tell you that's natural log. Maybe you didn't need to be reminded of this, but maybe you did. So that's just some kind of remedial Precalc type stuff. What bearing does that have on this problem? I should note some restrictions here. One restriction is that t must be greater than or equal to 0. Fact. Greater than 0, because I can only take the natural logarithm of a positive number. So that's one thing. I feel like there are no further restrictions, because as we can see, the range of the natural log function is everything from negative infinity to infinity. So sort of all x values are possible. And I think y can also be 0, right? Because if I plug in 1 to t, ln 1 is 0. So I think the only thing to say about y is that it has to be, can't be negative. Okay, so those are my restrictions on t and on y. What's the sort of next step? The next step is the end behavior step. And okay, so let's do that. Here I will stop writing nonsense. I'll just write good things, because of course t has to be positive, so it doesn't make any sense to consider the left end behavior. So we should consider what happens to x and y as t goes to infinity. But as a follow-up to this problem, it's really at this stage that you should also not just consider what happens when t is big, but also consider what happens near values of t where x and y themselves become huge. And I think it's pretty clear that something kind of crazy happens near 0. And so we do need to consider, and this is the time to do it, what is the behavior of these two curves near t equals 0 plus. Okay, well, what happens as t approaches infinity? Well, the natural log function grows very, very slowly. It takes, I need to go out to like, billions just to get 20 high or something like that. But it does continue growing and growing and growing. And so x will go off to infinity, if I plug in sort of e to the 10th, it's only 10. If I plug in e to the 100th, an astronomically large number, it's only 100. But eventually we will sort of slowly, x will continue to grow, because the natural log function does just keep growing and growing. And what about y? Well, sort of same thing, right? Now just slightly faster. And, okay, how about as t approaches 0 plus? Well, I think it's pretty clear from my picture, so it's probably a good job that we did that. That when you take the natural log of a tiny, tiny positive number, it is a huge negative number. That's because ln of, what's an example of a tiny, tiny positive number? Well, something like, 1 over e to the 100th or something like that is a very, very tiny positive number. But here I'm just kind of doing some more remedial precalc, right? What is 1 over e to the 100? It's a tiny, on the one hand, it's a tiny, tiny positive number. On the other hand, we can write it as e to the negative 100. And the very definition of natural log is that it's the inverse of e. And so this is just negative 100. And so I think you see that this is going down to negative infinity. What about y? If this is outputting a huge negative, it's being squared, then we get a huge positive. Okay, so I did my restrictions, I did my end behavior step. Let's eliminate the parameter now. Well, okay, kind of big surprise or something. ln t minus 3. What do I get? I get x plus 3 is ln t, and then if you square both sides of this, you get x plus 3 squared equals ln t, quantity squared, and that's just y. And so once again, I have the same relationship between x and y, but there the sort of the similarities end, maybe, or I don't know. Let's go and graph it now. Can't make a straight line. I think I really gotta go in a minute or two. Well, let's kind of make our, I think I should just draw my parabola first, then add the points in. Just looks better that way. Okay, so there's my basic curve, y equals x plus 3 squared. This is parabola, move 3 to the left. Let me try to understand this. Well, when is x equal to negative 3? I think I kind of said this already, right? It's when t equals 1. The natural log of 1 is 0, and so here we go. At sort of t equals 1 is when I will get my vertex negative 3, 0. All right, and maybe now is a good time to just go right to sort of the end, right? What happens as t approaches infinity? I appear to be headed out this way, and as t approaches 0 plus, I'm headed out this way. So this is kind of crazy, maybe unexpected, maybe expected, but I'm already sort of skipping ahead to what I think is the conclusion, which is that here this entire parabola is being sketched out, and it's taking 1 second to do the entire left-hand side of the parabola, and sort of an infinite amount of time to do the right-hand side. Does this make sense? I think it does. We just need to now pick some kind of points to understand this a little bit better. And, all right, here a good point to pick might be just e. Because natural log of e is just 1. So if I pick e, then I get negative 2, comma 1. Haha. So here I am at this point, negative 2, 1, and this is t equals e. And maybe another thing to do would be e squared, because the natural log of e squared is just 2. So I get negative 1, comma 4. Alright, so this is kind of a review of this kind of thing as well, that we're getting sort of for free. So now I'm sort of getting kind of a better idea of this. And also this indicates kind of how long it takes for this right-hand side to happen, because well, if I want to get to 100, say, I need to plug in t equals e to the 10th, which is very, very big. Okay, how about the left-hand side? Well, now you have to kind of following up on sort of what we did here, right? Now, I want to sort of think of 1 over e, of course, is e to the negative 1. And so ln of e to the negative 1 is negative 1. What is that? It's just sort of 1 over e, which is, roughly like a third or something. So here we go. It's here at this little point. Maybe I should stick this one over here, because that's t equals 1. This is t equals 1 over e, or e to the negative 1. When you plug that in, you get negative 4, comma, the negative 1 when squared becomes 1. So you get negative 4 comma 1, and then this will be t equals 1 over e squared, which is really like e to the negative 2. So natural log of it will be negative 2, and that's why that is negative 5 comma 4. Okay, so if you followed all that, great. Kind of rushing a little bit now because I want to be done with this. Let's do number 9, and we'll call it a day. Not sure I'm going to be able to even finish this problem. Yeah, maybe. X. Okay. Okay, here we go. Number 9. We do it. X equals tan t minus 3. Y equals tan squared t. And I'm getting a little bit dark in here, but the lighting is holding up. Maybe we want more lights. Maybe that's worse. Maybe that's better. Who can say? Let's do it. A little bit on the fast side. There's so much to talk about here. The first thing to notice is that, once again, these are sort of periodic functions. And this is kind of a crazy periodic function, this tan thing. So maybe we just need a kind of a quick graph of tan. Well, there's a lot of ways to graph tan, but the normal way or something to graph tan is to think of it as kind of continuous on, well it is, on this interval from negative pi over 2 to pi over 2. And and maybe even there's some sort of these extra kind of points here. What is that? That's pi over 4, and that's negative pi over 4. And at pi over 4 it's 1, and negative pi over 4 it's negative 1. So these are just basic facts about tan. Now of course tan is periodic, so this function is just going to repeat. But the period of tan is pi, so we just get repeat, 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 repeat. Well, if the entire, so if the tan function is repeating every pi, then it means that the x-coordinate is going to repeat every pi. And I think if you square the tan function, it's going to repeat at least every pi, sort of, if not more often. I think it will also sort of repeat every pi, right? Sort of down and back up again or something like that, right? And therefore, what I want to argue now, maybe this is obvious, if the x-coordinate is repeating every pi and the y-coordinate is repeating every pi, then the entire shape is going to repeat every pi. And therefore, the sort of period of the entire shape is pi, which is to say that whatever, as t changes, the x-coordinate changes and the y-coordinate changes, sketching out in the xy plane some kind of shape. Whatever shape is sketched out by this pair of parametric equations is simply going to sort of do that again every pi. Therefore, for simplicity, I think it's best to pick a particular interval of length pi and just let's graph the curve on that interval of length pi and then just say and so on, because it repeats. Okay, and here, because the tan function is continuous on the interval from negative pi over 2 to pi over 2, I choose, and I notate this here, I choose to do this on the interval from negative pi over 2 to pi over 2. So what I'm doing now is I'm making the decision that I'm just going to focus on this particular interval of t values. Maybe it's even clearer if I say I'm only going to consider t values between negative pi over 2 to pi over 2. Then I'm going to know that wherever I end up at pi over 2, then it's just going to start kind of back over again after that and just do that same thing again and again. Okay, keeping that in mind, what are some restrictions? Well, I think now there just kind of are no restrictions, right? Because for all the real numbers on the interval from negative pi over 2 to pi over 2, tan takes on all real numbers on those intervals. So I can take the tan of anything on that interval. If it makes you feel better to say, that t can't be pi over 2, okay, that's true, but that is true. You can write that down if you want. And then I guess also, y is going to be positive. But what's, I think, the tricky part now is the end behavior step. And of course, there's no end behavior really in the traditional sense of end behavior because as t goes to infinity, this curve just keeps repeating itself over and over again. So what we really need to be looking at is where x and y get crazy. And x and y will get crazy when tan gets crazy. And when does tan get crazy? Well, it becomes kind of infinite at near its asymptotes. And therefore, I need to consider what happens as t approaches negative pi over 2, and as t approaches negative pi over 2, and as t approaches pi over 2. But being kind of careful about this now, I really want to consider specifically what tan is doing just to the left of pi over 2. So as t approaches pi over 2 minus, and as t approaches negative pi over 2 plus. Don't be confused by this. Negative pi over 2 is the number. The plus just means a little bit more than negative pi over 2. Okay, so once you understand that that's what you need to do, actually answering the questions I think is not hard because we happen to make the graph, and if you hadn't made this graph, then you either should make it or just think of the graph in your head. But I think the answers to these questions become obvious, right? Here, just a little bit more than negative pi over 2. X, which is just tan, is going to negative infinity. And what's happening to y? Well, I'm going to have some negative huge number, but it's being squared, and so it's going to be positive huge. And, okay, great. How about as t approaches pi over 2 minus? Well, my picture is telling me that a little bit less than pi over 2, x is going to infinity. And y is also going to infinity because you're just squaring something that's really big. All right, at this point I kind of can go wrong almost, and now let's eliminate the parameter. Well, x equals tan t minus 3. Well, we get x plus 3 equals tan t. And if we square both sides, we get x plus 3 squared equals tan squared. And that's y. So once again, it is the parabola y equals x plus 3 squared. And, well, let's just graph it now. So, 1, 2, 3, 4, 5, 6. And we got all of our parabola, getting more savvy with this. Since I can't draw parabolas, no one will know. Man, that's so bad. When did I make a math teacher? Okay. Good. So there's a point, and there's a point, and there's, oh man, a point. Maybe I'll try to, it really should look better, and by that I mean like, right and stuff. There we go. I kind of needed more curvy. Okay, so what's happening? How is it happening? That's really our question. We're going to need to do some kind of point plotting and stuff, or maybe we should just kind of go in order. What's in order? Well, at the beginning of time, a little bit more than time negative pi over 2. Where am I? I'm at negative infinity comma infinity. So therefore, I'm up at the top left-hand corner of this parabola, so to speak, at time t equals negative pi over 2 plus. And as t approaches pi over 2 minus, I'm up here. Okay, so I already kind of feel now that what this must be doing is just going kind of in order, sort of down this thing. What else sort of could it be doing? And that's just right. Let's plug in some more points to sort of see what's going on. Well, I don't know, 0 seems like a good decision. Tan of 0 is 0, and so if I plug in t equals 0, then indeed I get negative 3, 0. That's kind of comforting. What's another nice number I could plug in? How about how about pi over 4? As I mentioned, that's just like a known thing, right? That tan of pi over 4 is 1. That's just, you know, at the 45-degree point on the unit circle. So tan of pi over 4 is 1. If I plug in pi over 4, I get -2. -2 comma, and here you have 1 squared is 1. So here I am at -2, 1, that's t equals pi over 4. And I don't know if there are any other good numbers, really. I mean, there are things that you can do. You can plug in, I don't know, pi over 3 or something, but you just get like √3. I don't think I need that in my life. So maybe just negative pi over 4. What's tan of negative pi over 4? It's -1. So here I would end up at t equals negative pi over 4. Here at -4 comma 1. And so I think that's about all I need to do, right? We start at time negative pi over 2 plus. I go down, it takes me some amount of time to just from negative pi over 2 to negative pi over 4 to get to this point. Then it takes me from negative pi over 4 to 0 to do this little jump jump. Then it takes me from 0 to pi over 4 to do this little bit, and then from pi over 4 to pi over 2 up there. Okay, there's one last thing which is to note, which is that this thing repeats every pi over 2. And so as soon as I hit pi over 2 minus, where do I end up at pi over 2 plus? Instant teleportation back again. So this, I think these teleporters are kind of essential to indicate that, in fact, what's really happening in this problem is that we're going like instantaneous teleportation from the top right-hand corner of the parabola to the top left-hand corner of the parabola, as sort of over and over again, and this entire thing just kind of repeats every pi forever. Good. This whole entire lesson was supposed to be, well, an introduction to parametric equations, a bunch of examples of using parametric equations, the importance of kind of considering end behavior, this sort of relative unimportance, low importance of simply knowing the relationship between x and y that you get from eliminating the parameter. That's just kind of one small piece of the puzzle. Also a review of natural log functions, a review of tan, a review of some other things. So I think this was all great. Hopefully you watched the whole thing. Goodbye, class.